Welcome back, everybody. In today's video, you're going to see a real-world example of deep reinforcement learning. Let's get started. Now, this video was motivated by a question from a student from my deep reinforcement learning course, which, by the way, is on sale for $9.99 for the next few days, should you be so inclined. Student says, I've been going through your course on Udemy. It's been a great supplement to my endeavor to learn RL. Would recommend it to anyone else who's trying to learn reinforcement learning. Well, thank you, Larry. I appreciate the kind words, but let's get to your question. An area that I've been struggling with is understanding how to frame arbitrary decision tasks as an MDP, a Markov decision process. I'm currently reading a paper and using RL to optimize query execution plans. In that paper, I'm finding it difficult to understand how the state space works. Would you be able to make a video going through some examples of framing decision tasks as an MDP? An area of interest for me is job scheduling. Well, Larry, you are in luck. I managed to read the paper and achieve some level of understanding of it, at least well enough to explain the setup and the state space for the purposes of this video. But first, let's address your question of the arbitrary task for a Markov decision process. So you may get hung up on this, and this is something when I was doing a consulting gig for marketing company that want to use deep Q-learning for optimizing bids on dynamic search ads as well as text-based ads in the Google search engine. They were kind of hung up on framing the particular problem as a Markov decision process. Now, the way I think of it, and this may be a little bit fuzzy or incorrect, but the way I think about it is that the Markov property is a property of the system. Does the system depend only on its prior state and the action taken by the agent? If yes, it has a Markov property. It is a Markovian type system. And that allows you to apply all sorts of mathematical machinery, in particular the mathematical machinery of reinforcement learning, to solving the problem. You don't really construct a Markov decision process. A system is Markovian. So that's a little bit of confusion there. And by virtue of having the Markov property, you are able to use all of the beautiful machinery of reinforcement learning to solve problems, in this case optimization of SQL queries in a database, which is actually a pretty cool application, something I hadn't thought of. So I hope that kind of clears that up. If you are asking about practical applications, how to do it in practice, typically you would construct a memory of the episode of the actions taken, states encountered, and rewards received. Those could be represented as an array of tuples if you want. And that is used to train the agent over time using whatever algorithm. In this case, they're using something called PPO, proximal policy optimization, which we haven't covered on this channel quite yet, but it is a form of policy gradient methods. So with all of that said, let's go ahead and get started with the paper. It says, we'll read the abstract first. It gives you, if you don't know how to read papers, the abstract kind of tells you what it is about, what you can expect from the paper. It says joint order selection plays a significant role in query performance. However, modern query optimizers typically employ static joint order enumeration algorithms that do not incorporate feedback about the quality of the resulting plan. Hence, optimizers often repeatedly choose the same bad plan as they have no mechanism for learning from their mistakes. Here we argue that deep reinforcement learning techniques can be applied to address this challenge. These techniques, powered by AI, artificial neural networks, can automatically improve optimizer decision making by incorporating feedback. Towards this goal, we present rejoin, a proof of concept join enumerator, as well as preliminary results indicating that rejoin can match or outperform the PostgreSQL optimizer in terms of plan quality and join enumeration efficiency. Now, if you don't know what all that means, don't feel bad. I am no SQL database expert. I know the bare minimum of how they work and a little bit of how to query them and get data for them because I've had to do that. What this is saying is that the way in which you query a database to determine relationships between objects in that database. So let's take an example. Let's say you have a database of customers that have purchased from your business. You run an e-commerce store, something like that. And through Google Analytics, as well as other tracking software, which we all use, or at least anybody running a business certainly uses, you have some information about that audience. So for me on YouTube, I have information about not about any individual user, but as a bulk set. So in my case, for analytics, I know the age, the gender, perhaps some other interests of the audience. But if you're running an e-commerce store, you might know a little bit more. You might know an IP address. You don't have an individual identity, but you can associate an IP address with a specific customer, as well as things like age from your analytics, whether or not they purchase, estimated income perhaps, as well as other on-page buying, on-page behaviors. If they scroll or if they click, these are things you can track and know as a good data scientist and someone who runs a website. And so if you want to find all of your customers that meet some set of demographic criteria, say all males above a certain age that make a certain amount of money, and you query that database, the order in which you query those parameters actually matters with respect to how long it's going to take for getting that data out of your database. And of course, time is money, time is efficiency. And so it's very important to minimize the amount of time taken for joint order enumeration. And the problem they're attempting to solve is that existing algorithms don't incorporate any feedback mechanisms. So if the strategy you choose at the beginning of how you're going to do your query sucks, you're just kind of stuck with it. You can go back and try to change it, but that takes time. And are you going to gain back the lost time in trying to tweak that process versus what you lose in the query? It's unknown. It's something you have to decide or figure out. But their proof of concept algorithm here actually allows deep reinforcement learning to optimize the query time over time, which is awesome. I think that's a great use case. I may use PostgreSQL, which is there's MySQL, PostgreSQL, SQL. There's a few different types of relational databases. So let's scroll down and read a little bit of the introduction. Now, the introduction is where you're going to find some background material to set up why they are trying to solve the problem, where other solutions fall short, right? Because if every other solution out there was perfect, then there would be no need to write the paper. So the authors have to present their case for why their particular plan is needed. So it says, identifying good joint orderings for relational queries is one of the most well-studied problems in database systems, as the selected joint ordering has a drastic impact on query performance. A primary challenge of joint order selection is enumerating a set of candidate orderings, meaning saying, here's a set of possible ways I can query those selected parameters, the demographics, the age, etc., and identifying the most cost-effective ordering. Searching a larger candidate space increases the odds of finding a low-cost ordering at the cost of spending more time on query optimization. There are no free lunches, people. If you spend more time trying to figure out how to query the database, that must be taken into account in terms of the total efficiency of what you're doing. Joint order enumeration thus simultaneously seeks to minimize the number of plans enumerated and the final cost of the chosen plan. Traditional DBMS, I guess that stands for Database Management Systems, employ a variety of joint enumeration strategies. For example, System R uses dynamic programming to find the left deep join tree with the lowest cost. Not entirely certain what that means, honestly, while PostgreSQL greedily selects low-cost pairs of relations until a tree is built. Now, that's what they're trying to beat, the PostgreSQL optimization. And it says many commercial products allow the database administrator, the DBA, to control the size of the candidate plan space via structural constraints or by cutting off enumeration after some elapsed time. Okay, so it allows administrators to kind of decide how they want to do the queries. Pretty cool. Unfortunately, these heuristics often miss good execution plans. More importantly, traditional query optimizers rely on static strategies, meaning they don't change over time, and hence do not learn from past experiences. Traditional systems plan a query, execute the query plan, and then forget they ever optimized this query. That's a problem. Because of the lack of feedback, a query optimizer may select the same bad plan repeatedly, never learning from its previous good or bad choices. In this paper, we share our vision of a learning-based optimizer that leverages prior experience, aiming to learn how to optimize future queries more effectively, i.e. better query plans, and effectively meaning less time on optimization. We introduce a novel approach to query optimization that is based on deep reinforcement learning, DRL, a process by which a machine learns a task through continuous feedback with the help of a neural network. We are no strangers to that here on this channel at Machine Learning with Phil. That is what we do here. We do deep reinforcement learning for the most part. We argue that existing deep reinforcement learning techniques can be leveraged to provide better query plans using less optimization time. Okay, that's why they do it, because it's better than PostgreSQL. It's better than, static plans. That's their whole shtick. As a first step, we present rejoin and proof of concept joint order enumerator entirely driven by deep reinforcement learning. And it talks about what they've done. So we're going to go into it here. Let's take a look. So join enumeration says rejoin assumes, when we're right here, whoops, not what I wanted to do. It says rejoin assumes a traditional cost-based approach to query optimization used by many database management systems. Specifically, given a SQL query as an input, a join order enumerator searches the subspace of all possible join orderings and selects the cheapest ordering according to the cost model for execution. This enumeration does not perform index selection, join operator selection, etc. These tasks are left to other components of the database management system optimizer. A join ordering is captured by a binary tree in which each leaf node represents a base relation. Figure 1 shows 3 possible join orderings for relations A, B, C, and D. So let's take a look at this figure. So you have 3 different join orderings. So you have this symbol, this kind of X thing, kind of sideways hourglass symbol, I believe means the intersection of the 2 different sets. So intersection of A and C, and taking the intersection of that with B, and intersection of that whole schmear with D. And there are different ways you can do this operation, meaning that you can perform the intersections in different orderings. And there are 3 different examples here. And those different orderings are going to have a drastic impact on the query performance. Okay, makes sense. So reinforcement learning, this is something we all know. It's an agent interacting with an environment, receiving rewards, attempting to maximize rewards over time. All well and good. Next, we formulate the join order enumeration process as a reinforcement learning problem. Okay, so now they're making the jump from the database query problem into the domain of reinforcement learning. Each query sent to the optimizer represents an episode. So our episode is a single query. And rejoin learns over multiple episodes, i.e. continuously learning as queries are sent. Each state will represent subtrees of a binary join tree, in addition to information about query join and selection predicates. We'll get to that in a minute. Each action will represent combining 2 subtrees together into a single tree. A subtree can represent either an input relation or a join between subtrees. The episode ends when all input relations are joined, a terminal state. And they have a diagram for this momentarily. At this point, rejoin assigns a reward to the final join ordering based on the optimizer's cost model. The final join ordering is sent to the optimizer to perform operator selection, index selection, etc., and the final physical plan is executed by the management system. So this framework is shown in figure 2. So you have SQL database stuff, our different queries, for instance, that get vectorized into some initial state, and that's where our viewer, Larry, had a little bit of an issue, and I can see why. It took me quite a while to kind of parse out what they were doing, but it's quite clever, and I rather enjoyed figuring it out. Basically, they're vectorizing a set of relations in the database and passing that into the environment. Of course, that does all this stuff with deep reinforcement learning, where it selects actions, executes the actions, gets its reward, and updates its, in this case, it's a policy gradient method. It's going to update its policy to maximize its total reward over time. And the stuff from the environment gets passed out to the operator selection and execution engine to pass back in the reward to the, I guess I'm reading a little bit wrong, but it gets passed out to the operator selection and execution engine. Okay. So now we have an example, and that's down here in figure 3. We're going to take a look at this more in depth in a moment. It says, can I show both on the screen? Barely. Whoops. Not now. Go away. Okay, so figure 3 shows a potential episode for a query involving 4 relations A, B, C, and D. The initial state is thus S sub 1 equals the set A, B, C, D. Okay, so let's scroll down here. So we have 4 blocks here, A, B, C, and D. That's our initial state, 4 different relations. And the query we're executing is select all, select star is the character for all, from A, B, C, and D, where the ID of A equals the ID of B, and the ID of A equals C, and the ID of C equals the ID of D, and B sub A2, where A sub 2 is some element in B, is greater than 100. So what they're trying to optimize is the execution order of these where statements. Does it matter if you select A.ID equals B.ID versus A.ID equals C.ID? Do those matter? Does that order matter? We don't know. That's something they're trying to find out, and that is the point of the whole problem, because evidently, this is a trivial example, but we're going to take a look at some other examples momentarily. But this is a fairly big problem in database management systems, and they're attempting to solve it. Let's scroll back up. So it says right here, the action set A1 contains one element for each ordered pair of relations, e.g. 1, 4, a tuple 1, 4, subset of A1 represent joining A with D. So A is represented by 1, D is represented by 4. So the action 1, 4 represents the join, the intersection of A and D, and 2, 3 represents joining B with C. So in our thing down here in our figure, it says the agent chooses the action 1, 3, representing the choice to join A and C. The next state is therefore S sub 2 equals A intersects C, comma B, comma D. So let's come back down here and take a look. So we have A intersects C, that's this sideways hourglass operator here, and then you have B and D. Don't worry about the rest of this stuff on the bottom here, the vectors and matrices, we'll get to that momentarily. Okay, all well and good. So that's how we're representing the state graphically. The agent next chooses the action 2, 3, representing the choice to join B and D. So scroll down here, and so now in state, the next state we have the intersection of A and C and the intersection of B and D, but no relationship between those two separate subtrees. So this is just 4 little nodes sitting out here, and then you have in the second from the left pane, you have one subtree and then 2 other little nodes, and now you have 2 subtrees. Okay, so now it says at this point the agent has only 2 possible choices. A sub 3 equals joining 1 with 2 or 2 with 1. Supposing the agent, that's because you have right here you have 1 and 2, right? You have A intersects C and B intersect D, so it's only 1 or 2, 1, 2 or 2, 1. Supposing the agent selects the action 1, 2, the next state 4 is A intersects C intersect B intersect D, which is this. So you add an extra node, and that's important. Okay. And this state represents a terminal state. We are right here. Scrolling up, it says, at this point, the agent will receive a reward based on the cost model's evaluation of the final join ordering. Now, this is where our viewers' confusion comes in, and I understand why. It is quite confusing. So let's start reading the state vectors, because this is, and I'm going to pause here for a moment. Now, this is one of the hardest parts about applying deep reinforcement learning to real-world problems. You have some database of data, and they're going to use the IMDb data set, so you have a database of information about movies of all things, right? And how do you represent a database of information about movies as something you can pass into a deep reinforcement learning model? And in particular, how do you represent the SQL queries of those properties as something you can feed into a deep neural network? As you know, deep neural networks don't take too kindly to data with wildly differing scales, doesn't take kindly to certainly data with different data types, so you can't pass in characters, integers, and floats and expect to get a reasonable result or even something that will actually properly run. So you have to be very careful in how you design your state vectors and your state space and your action space in particular, as well as your rewards. They'll talk about the reward. Did they talk about it? Oh yeah, it's right here. It says the reward based on the agent's cost model, and they don't have a reward associated with intermediate steps. So there is no reward for minimizing the number of queries. There's only a cost based on the final output. Just something to note. I don't know if it really matters. Probably not, but either way, that's just what we're dealing with. Okay. So it says rejoin requires a vector representation of each state that captures information about the join tree structure and the join selection predicates. Next, we outline a simple vectorization strategy which captures this information and demonstrates that reinforcement learning strategies can be effective even with limited input data. Very, very cool. Okay, here's the hard part, the tree structure. So at least I'm assuming that's what he's talking about. That's what I found difficult. Maybe he thinks this is easy and there was something else that he found challenging, but to me this was the hard part. To capture tree structure data, we encode each binary subtree, meaning join ordering decided so far, X is a subset of S sub J, as a row vector V of size n, where n is the total number of relations in the database. The value V sub I is 0 if the ith relation is not in X and equal to 1 over H as a function of I sub X of I and X, where H Ix is the height of the relation R sub I in the subtree, X the distance from the root. Now that's where some confusion came in. I'm not certain on their definition. I'm going to point to something else that makes me rethink that and is more consistent with what I see in the paper, at least the graphic that they give. So it says, in this example, in figure 3, the first row of the tree vector for the second to last state, A intersects C and B intersect D, corresponds to A intersects C. The third column of the first row is a value of 1/2, corresponding to C having a height of 2 in the subtree. The second column of the first row has a value of 0 since the relation B is not included in the subtree. So they're talking about, let me double check to make sure I don't mislead us here. They're talking about the third column of the first, okay, so in the example in figure 3, the first row of the tree vector for the second to last state. Okay, so right here, this state. Can I highlight that? No, I cannot. Well, yeah, I can. Kind of this state. No, that doesn't work. Second to last. You get it. You get the idea. So here we have A intersects C and B intersect D. So this is represented by a 2-row vector of 4 columns. There are 4 columns because there is an A, B, C, D. Notice that as you read from left to right on the tree vectors, there are always 4 columns. However, the number of rows decreases successively as we take more actions. And in particular, let's start from the left because it's a little bit easier. You have no relationship at all between A, B, C, or D. So this is the identity matrix, ones along the diagonal. Okay, that seems more or less logical. However, in the first panel from the left, you have the agent has taken the action 2, 3. It has joined, it just performed this following action 1, 3. So it has joined A and C, and so you have the intersection of A and C as well as B and D. So then you have this vector, this matrix here that is 4 columns and 3 rows. There are 3 rows because there are 3 distinct things here. You have the intersection of A and C, then you have B and D sitting by themselves. That's where the origin of the 3 rows comes in. However, where do these, if you can read it, these are 1/2s. And I'll leave a link to the paper in the description so you can read along. But these are 1/2s. Where does that come from? Well, if you take a look here, it's a 1/2 between A and C, and the B and D elements are 0. The B and D elements are 0 simply because there are no connections between this intersection A and C, and B, the intersection of A and C with B and D. There are no connections between those, so they're just off in La La Land doing their own thing. A and C have a value of 1/2 because we have the longest distance. So their definition is a little bit misleading. Let's take a look at Wikipedia. It says the height of a node is the length of the longest downward path to a leaf from that node. The longest downward path. So if we take a look here, the longest downward path from A to C has 2 edges, 2 little lines here. So 1, 2. So it's 1 over 2, so 1/2. And that's symmetric with respect to A and C. So then we take a look at this next one, and it says we have 2 things, the intersection of A and C and the intersection of B and D. And so there are two lines connecting A and C, but no lines connecting A and B or A and D or C and B or C and D. Likewise, B and D are connected by 2 lines, but there are no lines connecting B and D to either A or C or any combination thereof. And so we have 2 things, hence 2 rows, each with a vector, 4 columns. A intersects C is 1/2, 0, 1/2, 0, and B intersect D is, as you might expect, 0, 1/2, 0, 1/2. Okay, that makes sense. Now, where the confusion comes in is in this final step. So in the final step, we have the intersection of these 2. So you have this extra node here that takes the intersection of A intersect C and B intersect D. So then it goes to 1/2. Now, if you're looking at this thing, you might be questioning why. If you take a look at their definition, it says the distance to the root right here, the distance to the root. So that's a little bit misleading. Now, I'll point out something else in a moment that leads me to believe they made some careless mistakes in their wording. This is by far not a perfect paper, but it's a cool concept, and I don't doubt the veracity of the results. I just wish they had taken some more time to polish it up. But anyway, so why is this 1/4? Why is it not like 1/3, for instance? Why is it 1/4? Well, let's take a look here. So it's the maximum distance between a node and a leaf. So the maximum distance, not minimum. So let's take a look here. We have how would we go from the, let's say, A all the way to D? So you'd say we'd have to go up 1, 2, 3, and 4. We would have 4 lines to traverse. We'd have to go along the outside perimeter of this tree structure. So that's the longest distance. Likewise, from any other, if you take a look at it and prove to yourself that it's 4 nodes, 4 edges from any node to the furthest node. So that is the 1 over h, 1 over height. That's where the confusion came in. For whatever reason, that took me forever to figure out, to kind of parse through it. You know, for a while I thought it was just 1 over the depth squared because it's a binary tree, but that's not correct. Actually, maybe that ends up being right, but now it's late at night, I can't think straight. So the basic idea, it is the number of edge lines that connect each node in the structure. Okay, so that is one part of our state vector. What about anything else? We also have this b.a2 greater than 100. So let's scroll back up and think about that. And here's where I think they kind of screw up a little bit in their, at least text. So pay attention here. It says join predicates. It says to capture critical information about join predicates. In other words, a join predicate, if you don't know, a predicate is just a conditional. So join conditionals where A equals B, A.id equals B.id is a join predicate. Okay. And likewise, B to C or C to D, whatever they were. The join predicate is just a conditional statement, in this case, a where clause where 2 things are equal to each other. We create an n by n binary symmetric matrix M for each episode. The value M sub I sub j is 1 if there is a join predicate connecting the ith and jth relation. Remember, the A, B, C, D are the relations. And is 0 otherwise. This simple representation captures feasible equijoin operations. Figure 3 shows an example of such a matrix M. The value M21 equals M12 equals 1 because the predicate A.id equals B.id. The value M23 equals M32 equals 0 because there is no join predicate connecting B and C. So let's take a look. And so we have where AID equals BID. So in this row A, you have a 1 connecting the A and B right there. And there is also a relationship AID equals CID. And so you get a C here. Okay, but there is no explicit relationship connecting A and D. And so there's a 0 there. And notice that it is symmetric about the diagonal here, and those are all zeros. There's no relationship between an element and itself because they're equal to itself by default. Likewise, we have BID equals AID, so there's a 1 here, and that is it because there's no other stipulation on BID. And there is AID equals C and CID equals D, so you have a 1 here indicating the AID equals CID, and the CID equals DID. And the only relationship for D is where it's equal to C, so there's a 1 there. Okay, so that is the, what do they call it here? They call it join predicates, but then down here they call it column predicate vectors. So they're calling it a different thing. The meaning is clear based on what you read, but it is not at all clear. And in fact, it's actually backwards. So this says join predicate, and this is the join predicate. So they call the actual join predicate something else, and they call the selection predicates, which is this thing, and I know it's this thing because it is a k-dimensional vector, not a matrix. This thing is the selection predicate, and this is the join predicate. Okay, so this is where they screw up their nomenclature. That's what makes me believe that they screwed up their nomenclature. Here when they're talking about the distance from the root, it's the maximum distance from each node from a node in its leaf, and this is just computer science. This is not specific to databases. This is computer science, which, brief interlude here, if you don't know much about computer science, I want to recommend a book. Check out this book on Amazon, Computer Science Distilled. It's not a very thick book. It is very concise, but it contains pretty much all of this kind of stuff, everything about binary trees, graphs, hash tables, databases, computer architecture, algorithms, all the stuff you need to know to have a solid foundation in computer science you can find as a summary in that book. But I digress. Okay, so next we have selection predicates. The selection predicate vector is a k-dimensional vector where k is the total number of attributes in the database, the total number of attributes across all relations. So all the relations from A, B, C, and D. So if each one has 1,000,000 relations, the selection predicate vector has 4 million relations. The ith value is 1 when the ith attribute has a selection predicate in the given query and 0 otherwise. This reveals which attributes are or are not used to filter tuples. For example, figure 3, the value corresponding to b.a2 is 1 because the predicate b.a2 greater than 100. So we have this here, and b.a2 greater than 100, a filter where you want to filter results by the value in b.a2, and no other elements in the other relations, so other databases, A, B, C, D, or whatever they are, tables. And so you have this selection predicate vector, not the join predicate vector. This is the join predicate vector, but this is the selection predicate vector, and you have b.a2 equal to 1, and all the others are 0 because there is only one filter, one greater than symbol, less than, or equal to, for a specific element of a given table. Okay, so I'm going to kind of talk a little bit about the rest of the paper here. I'm going to talk about the results and skim over it. I'm not going to implement this yet. I'm thinking about doing it later on when I get to PPO, because this would be a really cool project to implement. The data is open source, and I think there's enough information here, but they do leave out one important detail and probably where this guy also may get confused. So you have one problem, and I'm not certain how I would solve this, is that the state vectors are going to have varying lengths. So each step of the episode, these tree vectors decrease in the number of rows. So that's kind of an interesting problem. I don't quite know how they're going to solve that. The other thing is that you're dealing with a matrix here, a vector here, matrices here, and a vector there. So how would you deal with that? Well, if you think back to like my videos on where we do a neural network from scratch, where we use the MNIST dataset, where you have a series of images, how do we handle turning images, which are matrices, into data we can feed into a regular deep neural network, not like, say, a convolutional neural network? Well, we deal with that by just flattening it, disassembling it, taking the first row like that, second row, appending it to the end, third row, appending it to the end, etc., etc. So you just take the matrix and flatten it into a vector. And they can do something like that here. The downside is you're going to have vectors of different lengths, so your input size is going to change over time. Now they may do masking of some kind where they input dummy values. I don't know how they're going to handle that, but the way you're going to handle the vector to because we're not going to be using convolutional neural networks, we're going to have to use regular deep neural networks, and they talk about that in a moment. But the way we're going to deal with that is by just flattening all these matrices and turning them into vectors and feeding them to our deep neural network. So that is my breakdown of the state vectors. That is how I analyzed it. If I'm wrong, I make no statement that I'm right. I just spent about an hour reading over this, and this is what I came up with. If I'm wrong, then I'm wrong. Leave a comment down below if you think I'm wrong. I'm open to other arguments. But let's go ahead and read out the rest of it just to skim over it and see what else they have. So they talk about reinforcement learning, which we know about, aims to optimize the policy pi sub theta over episodes. In other words, to identify the policy parameters theta that optimize the expected reward. However, the reward is typically not feasible to precisely compute, and hence policy gradient methods search for the optimal policy parameters by constructing an estimator of the gradient of the reward. Okay, so it's a policy gradient method. And the policy is, in this case, the probability of selecting a given set of actions. So in this case, the set of possible actions are 1, 2, 1, 3, 1, 4. That's not clear to me either. Does the set of actions, possible actions, correspond strictly to the join orderings, or does the set of all possible actions correspond to all possible join orderings that don't necessarily correspond to the given query? That's not entirely clear. I would wager that the action space corresponds to the only possible ways of configuring the system, because the join orderings here are 1, 2. There is no AC equals B, so I'm guessing it's just all the possible combinations. So you'd have 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4 for the possible actions in the first state. But I could be wrong there. That's something I would have to play with or even email the authors to find out. Okay, so Given an estimate E, gradient descent methods tune the initial parameters theta by increasing each parameter theta sub I by a small value when the gradient is positive. Positive gradient indicates a larger value of theta sub I will increase reward, and decreasing it by a small value when the gradient is negative. Okay, blah, blah, blah. We know all this. If you don't know all this, check out my videos on policy gradient methods. You'll learn all of this in those videos. So let's talk about the what they used, which is really cool. They use a database size of 11 gigabytes from the IMDb dataset, 4 gigs of RAM on a VM with 2 cores, and a maximum shared buffered pool size of 1 gigabyte. And they configured it to do something I don't really know about. And they use proximal policy optimization, PPO. Okay, and they use 2 hidden layers with 128 rectified linear units each. Okay, pretty cool. So they use a pretty shallow network, 2 hidden layers, 128 units. That's pretty basic. Let's just go ahead and take a look at the results because I'm not going to read the rest of the paper. What's really cool is you see this plot here and it has the convergence. So you see that in the very beginning it performs really poorly. That's purple line is the algorithm and the teal line is PostgreSQL's optimizer. And so the query plan as a percentage of the PostgreSQL is what they're looking at. In other words, how quickly does it converge to the PostgreSQL? And you see that after about 8,000, 9,000 episodes, right here, it kind of converges to the performance and in fact beats the performance of PostgreSQL. So that is encouraging. At least in some conditions, it does better than the optimizer built into PostgreSQL. That's very cool. So they have this other cost of join orderings. So I'm guessing lower is better. And you can see that Postgres is purple, rejoin is blue. You can see that in most cases it is better. The blue is lower than the purple in most cases. In some cases it's higher. And these queries, let's take a look at these really quick so you know what we're dealing with. So these are specific queries from the benchmark. So they're using a benchmark here, which is the join order benchmark for PostgreSQL, and it uses the IMDb database. You can find it here, but there's a number of different queries and they're labeled rather inconveniently, but let's take a look at a few of them to see what we've got. So you have select, I'm only going to scroll here. So select min mi.info as release date. You got a bunch of select statements from different tables where a bunch of relations are true. Okay, so much more complicated than what we have in the trivial example they give in the paper. So if you scroll through them, you can see that the select stuff changes. This is 13A, 13B, 13C, 13D. You can see that the select statements change as well as the where statements, but the from statements remain all the same. So those are the templates they talk about in the paper. If you go to read the paper, they talk about templates. But you can see the cost for PostgreSQL is sometimes higher than the rejoin algorithm. And it has overall lower latency in most cases, and the optimization time is significantly lower in most cases. So that's as far as I wanted to go, but I wanted to show you a real-world use case of deep reinforcement learning to an actual problem. Proximal policy optimization is a cool algorithm. We're going to get to that in the future. Something I'm working on, not yet, but I will be working on. I'm working on A3C first, and then I'll work my way up to solved after critic and PPO. But it's a powerful algorithm. It outperforms deep Q learning in many cases. And that's because it's often easier to learn the policy than it is the value function. But this is a real-world example, and it shows some promise, and this is something that could maybe commercialize down the line. Maybe that's what the professor is thinking about. This is an academic paper that's from Brandeis University. I'll leave a link to the paper in the description, and as well as a link to this benchmark that they used. And of course, I'm going to leave a link to my discount code for my new course, Deep Q Learning from Paper to Code, where I will show you how to go through 3 separate papers and not just analyze them, but turn them into code specifically. PyTorch code. We're going to beat the games from the Atari library as well as a couple other environments. I show you how to do it all in the course as well as give you a brief overview of the fundamentals of reinforcement learning and the fundamentals of deep learning as well, because it's kind of an intermediate level course for people that are well versed in Python but not necessarily deep learning or deep reinforcement learning specifically. That's on sale for $9.99 for the next few days. Click the link in the description and or pinned comment to buy it. If that's too expensive for you, by all means, hit the subscribe button, the bell icon. I look forward to seeing you in the next video. Oh, and before I go, if you want to see this implemented, leave a comment down below. It's something I would love to do, only if there's enough demand for it. Only if it's going to get views. I got to play the YouTube game, baby. But anyway, leave a comment down below, and I'll see you in the next video.